Hi everyone, thanks for being here. So I'm Alison, I'm supervised by Andres Marcos and also by Thomas Ott in Airbus. And I'm going to present the last results on the PhD, which has this big title, but it's basically, you can think of it as an autopilot to reorient a spacecraft on its orbit. So why is it important to have this program for space observation missions? So you can see 3 spacecraft here, and they all have the same needs, which are to perform a lot of maneuvers and to maximize the operational availability. So it means have time for observing during the mission and maximize the effective area, which is the size of the mirror. So in the end, our space telescope and the new generation that is coming, or that has come for the past 10 years, have these needs, and there are new industrial concepts to tackle these needs, and these are to have multi-body and multi-actuator spacecraft. So all this, so James Webb, Ariel, and Athena, for example, they all have in common to have different onboard instruments for observing a target, and they have a common mirror. So this is the new part, that this mirror can move. So it moves thanks to a high pointing accurate mechanism. You will see more about this later. And all of these spacecraft also have rigid and flexible characteristics due to the solar rays, for example, for Athena or James Webb, as you can see. And so why do we need research for this? So actually, what I just said, it means that we have some multi-body effects. So I did a benchmark multi-body, multi-actuator spacecraft from the literature review from the missions I showed you before. And we can say, okay, this spacecraft, they have in common this mirror, in blue, and the mechanism that orients the mirror is the green part. And now you can imagine that when you want to move from one target, from one star to the other star for the next observation, you will need to move not only the main body in orange, but also that mirror in blue. And then you will have some multi-body, multi-actuator effects, because you will move the mirror, so it will change your spacecraft inertia, and then it will change your attitude. So it means this is really the difference with common satellites that are usually known as single-body satellite. So for this, there are some objectives that arise, which are improve the maneuver time, having this in mind, of course, improve the maneuver time to have more than 85% of availability, which means it is expected that for 85% of the time, you observe a target. And the rest of the time will be to reorient the spacecraft. So for this mission, you can have 1,500 maneuver per year. So it's quite a lot of maneuvering, and under mission constraints. And you have to do this satisfying the line of sight requirements. So one objective will be the guidance, or was the guidance that I did last year. So it was to develop for this an autonomous guidance that could be run on board. So this was really the main part to tackle, that it could not be a convex optimization, or because it had to be run on board, because it had to be an autonomous guidance. The second objective is a robust modeling. So how we are going to tackle this multi-body effect is by trying to identify uncertainties in the system and design then a controller using a robust model having all these uncertainties into account. These uncertainties having the multi-body effects and the flexible effects of the spacecraft. And the last one would be the control. So have a robust and systematic control for this kind of spacecraft, satisfying stability and performance. So for the line of sight guidance, the problem is that since the mirror is usually a highly sensitive to thermal effects, you cannot look at the sun, but not at all. So we have this cone which is called an exclusion zone. And all of the mission I show you, and usually all the space telescope, have this kind of cone, and then the angle varies. So you're on the orbit like this, like the spacecraft is. You can turn freely around the axis that is shown here, and that's where you cannot turn more or less than 35 here degrees. That's for the benchmark mission. It varies, but it's usually this order of magnitude. And then you cannot turn at all around the ZB, because usually you have a sun shield, so it's really located to this axis, so it's like minus plus 1 degree. And considering this, so Airbus were following a state of practice solution, which is to start from a position. You will start from an orientation, you want to go to the next one, and to ensure that you will never see the sun, you go into this plane. So they were systematically doing these 3 consecutive maneuvers, which is really robust, but time-consuming. So that was the main issue here, because we want, as I said, to maneuver quickly. So what I did for this is, in this cone, you can see it, for the line of sight, you can see it as a rectangle that would be delimited by the angles that we have in the constraints. And then, having this rectangle, then we know that we can, if we start from one position in this rectangle, we want to go to another one, there is we can find a line between these 2 points, which is the direct path. So this is the theory behind the guidance I did last year, and that I presented. So I presented it at UCAS. I was finalist for the Base Student Award. And then it was recommended for a publication in ACTA, so we did it, and it worked. And so, then also Airbus implemented it and verified it in a mission simulator for this kind of mission. And they saw that we increased the availability by 2%, which corresponds to a reduction of time of more than 20%. So it was, now it's implemented in the simulator, so it was nice. And so this was the first objective. The second objective was the robust modeling. As I was saying, you have the mirror that moves. And in our case, or for James Webb and for Athena, for example, and some others, you have this kind of mechanism which allows to move in 6 degrees of freedom. So you can move really into the 3 translational and 3 rotations. What we wanted to know is to assess if the flexibility of such a hexapod, it's called like this, such a mechanism could affect the spacecraft behavior, could interact with the solar arrays flexibility, for example. So we were interested in having a stiffness, but this kind of mechanism is called closed-loop kinematic chain mechanism. So it's not ruled by differential equations, ordinary differential equations, but they're ruled by algebraic equations, because you have several points that are linked to the same body. So you have usually one additional equation that closes this, the loop, to say, okay, to go from here to here to here to here must be 0 in terms of vectors. So this is usually the additional one that makes it non-explicit. So we could have decided to try to solve it numerically. But for us, what we're interested in when we do control for spacecraft is to have a stiffness matrix that relate the force torques and the displacements. So we really are interested in having a roughly estimate of the stiffness of this mechanism. So we were not really interested in doing and we also didn't have it, the FAM model or a model for the whole structure. So what I did is we were starting the analysis from an Airbus output of a modal analysis for one leg. And so it's high dimensional and there are a lot of modes. But what I found from latest review results in robotics is that we can only consider the axial mode in traction compression for this kind of parallel mechanism. So this is what I did. I took the stiffness that I extracted from the Airbus study, And I did from this a 6x6 matrix. So stiffness, Cartesian stiffness matrix. So it's not the same stiffness than you guys use in modal analysis. It's a Cartesian stiffness. So again, this relates torque forces to displacements. And from this, the leg, you express it, it's expressed in the leg frame. So you express it in the global hexapod frame, and then you transport it to the platform, because in the end, we're interested in having the relation between force torques on the platform in red and displacement of this platform. So I do the same with all the legs, and then you add them because they're all expressed in the same frame at the same point. So it's similar. You can think of it like inertia matrices. We do the same to assemble them. So it's similar, and it's very modular. And now you can see that we have access to each stiffness of each leg, so you can add uncertainty to them. It's linear, but you can say, okay, we have an uncertainty in the length, for example, or in the stiffness of the leg, and then it will be included in the global K matrix. So then this K can directly be used in a dynamics formulation, as I was telling you, that we like to have, and it can be solved, this one, quite easily compared to the mechanism that we had. And and then it can be solved, and so I solved it for a response to an impulse, and we can simplify it into a sum of sinus of sine waves, and where we know the amplitude and the frequency. And so to verify this model, we needed to have a simulation tool where we could put this stiffness. So this is, I did it in an Airbus tool, and for the validation, I did it on Simscape because we needed to validate the model. Your verification is to see how accurate it is. So you need to really test the stiffness. But then, whereas for the validation, you need to see if it's kind of physical, what you did. So in Simscape, this is nice because Simscape can actually solve this kind of closed-loop kinematic chain.
10 minutes.
Yeah, okay. I'm almost done. Oh, okay. So this was it. And comparing, then you put an impulse and you compare the oscillations that you have with the two of them. And it turns out to be quite efficient. So this is what we are going to present to the next UCAS conference coming in July. For the last one, it's what is remaining. So now I have the model, I have the uncertainties, and we need to do the control design of this model with the uncertainties. I have a few conference papers and one journal article that I mentioned earlier. We are also hoping to augment the paper we will present at UCAS into a journal version. And I also submitted a 3-minute video for the thesis talk. Then I stayed mostly, it was, since it's with Airbus, this PhD, the stays I did were at Airbus, usually to either work on the simulator or verify the models. So this is it. And then as an additional activity, I was a system engineer of the first CubeSat, of a student CubeSat. So I was supervising a team of 20 students, and we could participate in the ESA FlyU satellite design booster program. So yeah, it was a good experience also. So thank you.